Welcome. In this video, I will state and prove a formula for the expected value and the variance for a binomially distributed random variable. Alright? So let's say we have this nice little variable here, x. It's binomially distributed with parameters n and p. Then we have the formula for the expected value, and I'll write it up here because I'm expecting this to be the place where I have the most space. We can calculate that as n times p. Alright? And the variance for this variable can be calculated as n times p times 1 minus p. And since n times p is the expected value, and q we can write as the probability of failure, which is 1 minus p, which is 1 minus the probability of success. Alright? To prove this formula, these formulas, I will use a lemma on combinatorics to calculate the some combinations. Okay, and the lemma will be this. The lemma is that if I take the choices and multiply by the binomial coefficient, including the choices and the options, I can write this as the number of options, and then the binomial coefficient where the options and choices is reduced by 1. Okay? I will actually prove this. It's a short proof, but just for good measure. All right? Alright, so I'll write the left-hand side as r times n factorial divided by r factorial times n minus r factorial. This is simply the definition of the combinations of r choices and n options, or the binomial coefficient, as whatever you want to call it. Alright, what I'll do is I'll take this r and I'll cancel the first factor in this factorial. It looks kind of weird, but hopefully it'll make sense when I continue. Okay, this n will go in front of the fraction. The leading n will go in front of the fraction. So we'll end up with this an n here, and we'll end up with an n minus 1 factorial and divided by r minus 1 factorial, since we cancel the leading r there. And then we'll do a little trick here. We'll actually subtract 1 here, and we'll add 1. Okay? Standard math trick, right? So this will be n minus 1, minus r minus 1 factorial. It's slightly ugly, but it makes sense. And this plus 1 is of course, it's minus 1. And what this is exactly n times the n minus 1 r minus 1 binomial coefficient. That wasn't that bad. All right. Now I'm just going to start the main proof here. All right. Maybe I should use the space a little bit better. So let's prove that. Okay, I'll use the definition of the expected value for any random variable, at least a discrete random variable, and it'll be the sum of the random value. Oh shoot! I have to move this over. The proof is done. You can scroll back if you need to see it again. So it's going to be the random value multiplied by the probability of attaining that random value. Okay? Alright. And r goes from 0 to n. It spans all the possible random values. Okay, let's put in the probability for binomial distribution. This becomes the sum of r from 0 to n of r times nr, probability of success to the power of the number of choices, and then 1 minus p, the probability of failure, to the power of the remaining choices. Yeah, cool. And hopefully it's obvious where this lemma comes in. It comes in right here, since we have this r times the binomial coefficient. Okay, so let's just use the lemma. I'll use the red to indicate that I'm using this lemma right now. And I'll do a small trick before I continue. If r is 0, this whole thing is 0, so I'm not really interested in that. So let's just start from 1. Okay. So r is equal to 1 to n, and we get an n, we get an n minus 1, r minus 1, and then the same thing over here. 1 minus p, n minus r. Wonderful. Okay. What I do now is I take, hopefully I'm not getting too low, we'll see. So I'll take an n and a p outside the sum. So I'll factor it out. Alright, so I'll have an r equal to 1 to n, and then I'll have a n minus 1, r minus 1, p, r minus 1, 1 minus p, to the power of n minus r. But I'll do the same trick I just did previously. I'll subtract a 1 and I'll add a 1. What this is exactly the sum of all the probabilities for a binomial distribution that has 1 fewer options. But it's still going to be 1, right? So if we consider this is just 1, all right? And the way we can consider this, I just remove this proof here, is we can actually continue this as the sum of k from 0 to m of an np here in front. And then we do an m k p to the power of k 1 minus p to the power of m minus k. All right, where m and k are just the same variables subtracted by 1. All right, and hopefully it's more obvious here that this is just 1, right? And then I get the result that I wanted. I wanted to show that the expected value is just n times p. Wonderful. Hopefully this is not totally unexpected. I mean, if we have a 10% probability that we have success and we perform the trial 1,000 times, we're going to expect around 100 successes in the long term, right? So, so this is not a surprising result. Expecting the variance not to be as intuitive, but the process of proving it is pretty similar. Okay, so let's take the variance of x, and it's simply the sum from r equals 0 to n, and then we take the distance to the mean, where mu is simply the expected value that we just calculated, and then we weigh it. I'm going to expand this this parenthesis here. And it's going to be r squared. We use the square rule, or whatever you want to call it, minus 2r mu plus mu squared. And still the probability. I'm not going to expand this yet because it's totally unnecessary. All right. Now what I'm going to do is I'm going to take these 3 terms and I'm going to expand this into 3 sums. And I'm going to flip this. I'm going to take this one first because that's a constant. That doesn't have this the variable, so to say. So that's going to be the most easiest one to deal with. Okay. So let's take the first one first. We can put the mu squared outside the parentheses, and then it's simply the sum of all these probabilities. Again, summing over the whole sample space just because it's one. Something has to happen. So, this is trivially this time, I would argue. Okay. We get the next one, which is, oh shoot, let's wait with this. Let's still take the constants out, so it's going to be minus 2 mu, and then it's going to be the sum of r times the probability of x is equal to r. I just did this. I just calculated with this. This is exactly the expected value, right? So this is mu, and what I really get is I just get 2 mu squared. And if I subtract that from mu squared, I get minus mu squared. All right. Beautiful. So what's left is simply the sum r squared. And now I'm going to put in the expression for the probability here. That's still going to be n over r, p, probability of success to the power of the choices, probability of failure to the power of the remaining choices. Yeah. What I'm going to do now is I'm going to use this beautiful red lemma up here. Again, it's so powerful. It's beautiful. Yeah, and since if r is 0, again, this term just cancels, I will still continue from r equal to 1. So, yes. All right, and use this lemma. R equal to 1 to n, and then we get n times r, because we use one of the r's for the lemma, and then it goes n minus 1, r minus 1. P to the power of r, 1 minus p to the power of n minus r. Wonderful. Hopefully that is legible. Okay. Right. Remove this, and I remove this. Right. We still have those mu squared, but I'm just going to focus on this for now because this is the interesting part at this point. Okay, so I have that beautiful little thing. I want to use the lemma again. The problem is that these two don't match. So I do this beautiful trick where I add and subtract something that allows me to use the trait again. All right. So what I do is I add, kind of continuing this. If you can imagine that. There's no equality, so I'm continuing this equation. So what I'm adding is I'm adding n times the sum of r minus 1, r, n minus 1, r minus 1, p to the r, 1 minus p to the n minus r, and then I'm subtracting this again. Alright, so let's put this n in here. N R. Oh shoot! No R. No R. No R. That would have been slightly catastrophic. You might notice that this is actually the same thing as if we take one of these p's outside again, we get minus 1 here, minus 1, minus 1, and this again is just 1. So this is actually what I've added here, it's just np. But I need this, this expression to rewrite this. Even though it's just m times p, I want this expression to be like this. Right? I'll use this np later, but for right now I need this expression, because what happens now, if I take this thing and subtract this thing, I can put all the common things, I can factor out all the common factors, and what's left is simply the sum from r equals 1 to n of, okay, we have an n in common, and then we have an r from here, and we just have a minus 1 from here, and everything else will be the same. Now I can use the lemma again, because now these match up. Isn't it beautiful? I love it. Another comment though is that in this process we've actually removed, this subtraction here has actually removed the first term here, because r minus 1 will be 0 when r is 1. So now we actually start at r equals 2. Yeah, okay, but let's use our beautiful lemma, and I'm going to focus on the last term alone here. I'm going to just remember that this NP is there. I've made that mistake multiple times before. Anyway, so we use this lemma again, so we get this, and we get n times n minus 1, and then we get n minus 1, and r minus, not 1, 2, and then we get p r, 1 minus p, and minus r. Wonderful. And we're actually almost done. We're close. We put the n, we put these two outside the parentheses. We can take 2 p's this time, and we get n minus 1 p squared, and we get the sum from r equals 2 to n of this thing, n minus 2, r minus 2, p to the r minus 2, 1 minus p, n minus 2, minus r minus 2. We do the same thing, we subtract and add 2. And again, this is the probability of the whole sample space for a binomial distribution with 2 fewer options. So this, again, this is 1. This is cancelled, okay? But if we take everything we've gathered so far, is we started with a mu squared. We subtracted 2 mu squared, right? We had this NP here. And then we have this thing here. Right? To conserve some space, I'm actually just going to subtract these. This is going to be minus mu squared. And I'm going to put in my expected value, which is n times p. So this is going to be minus n squared p squared plus everything, okay? All right. Let me expand this parenthesis here. So we get n times n squared, p squared, okay? This is going to be n squared, p squared, and then it was n times minus 1, so minus n p squared. Okay. Wonderful. So this cancels, and this cancels. And the remaining 2 terms have a common factor of n times p. What's left here is a 1, and what's left here is a p. Absolutely amazing. All right? I know this can be done by linearity, but I haven't presented that right now, and I like it. Proof of the variance from basic principles. Wonderful. If you have any comments or questions, leave them in the comments, and you can go to my webpage for a text version of this, where this video will also be posted. See you next time.